We're in Rosen section 5.4 on recursive algorithms, and in this video we're going to talk about an advanced sorting technique called merge sort, and we'll see how it can be constructed recursively, and then we'll do a complexity analysis on it. So the way merge sort works is by splitting the list to be sorted into two lists, and then treating them with the same treatment, and then eventually bringing them back together. So we keep splitting a list into two lists of equal length, and we keep splitting them and keep splitting them until we get down to a whole bunch of lists that have only a single element. And you can represent all of these elements as at the end of a balanced binary tree, as we'll see in a little bit. And then we bring all of these lists back together. We will merge them, and as we're merging them, we'll make sure that the elements are in increasing order, and then the process ends when all the sublists have been merged. And that succession is also represented by really a reverse binary tree. And the thing that we're going to be keeping track of is a number of comparisons to do the complexity analysis. All right, now here's the top level routine of merge sort. It actually has two procedures. This first procedure is the one where we break it into two different halves. We read in a list of length n. We find an index to be the midpoint that's n over 2 floor function, and we split the list into two different lists, call it a left list and a right list. And then we're going to sort these lists by calling merge sort twice. And once we get them back, we're going to call a merge procedure, which we haven't seen yet. So we split the list into two, then we sort each of those two lists, and then we merge them to get back. And now L, once we get it back, L will be sorted. What happens when n equals 1? Well, nothing. It just comes back as itself. And then we don't have any kind of return for this list, so we're basically assuming that we're keeping track of L outside of the procedure. Okay, so now let's talk about this algorithm merge. What happens when I merge two sorted lists, my left list and my right list? Well, the way it works is pretty straightforward. I create a new set called L, which is an empty list, and then I just look at the leftmost entries of L1 and L2, and if they're both not empty, I compare the leftmost entries of the first elements, and whichever one is lower, I put that on the right end of L. So I'm moving elements from low to high, from L1 to L2, into L. And if removal makes one of the lists empty, since they're sorted, all I have to do is take all the elements from the other list and append them. All right, and this is very important. If I have lists of length m and length n, then I can do this merge operation with m plus n minus 1 comparisons as an upper bound. Won't be more than that. And if they were both of equal length, say if they were n plus n minus 1, obviously that would be equal to 2n minus 1. Okay, so remember that merge has complexity m plus n minus 1 comparisons, where m and n are the length of the two lists. Let's do a quick example on merging two lists. I've got two lists here that are sorted. Left list is 2, 3, 5, 6. Right list is 1, 4. I look at the first element in each of those. I pick the lowest one and add that to my merged list. And now my first list is unchanged. Second list has lost its 1. I compare the first elements in both. I see that the 2 is there. I bring that over, and now my left list has gone down by 1. My right list is unchanged. Compare first elements. 3 is less than 4, so I pick that 3, add it to my merged list on the right. This right list is unchanged. Left list now has 2 elements in it. The right list first entry is the lower one now, so we add it. And that list is now empty, so we just take that 5, 6 and append it to the end of my merged list. And so we had we had 4 and 2 are the length of my list, and I ended up doing 4 comparisons. My upper bound would be 4 plus 2 minus 1 equals 5. So I did stay below my upper bound. All right, so let's use the merge sort and merge procedures to put this list in increasing order. We'll take that list and we'll divide it into 2 and divide each of those into 2 again. And we're keeping track of where everything is on this binary tree. And we haven't done any merging yet. We just keep calling this till we got lists of length 1 at every position. And now we start to call, the merge starts to act. So I'll take the 8 and the 2, I'll put them in the correct order here. And then I'll take the 7 and the 10, put them in the correct order here, and now I'm done at that level. Now I'm at this level. 2, 8, and 4 gets put together by the merge subroutine this way. 6 and 9. 7, 10, and 1 gets put together this way. 5 and 3 gets put together this way. Now I'm at the next level, and these 2 lists get put together like this using my merge routine. You can verify that yourself. These 2 lists get put together that way, and then finally, using that merge routine, these 2 lists get put together in the correct order. All right, so let's talk about the complexity of that. Why is this considered a good merging or sorting algorithm? You might remember, if you took Math 250, and you could take a look at Chapter 3 at the analysis, that brute force sorting techniques are big O of n squared, and big O of n log n is going to be better than that. So we're going to do the analysis with n is a power of 2. We can always add dummy values to make n a power of 2. So this is a perfectly fine approach. So n equals 2 to the m. So at the end, since we have this splitting process, we're going to have m levels before we get down to having 2 to the m lists, with each list having length 1. And then we start at that level, and we go from 2 to the m list to 2 to the m minus 1 list with 2 elements. And then we have to take 1 comparison to do each of those, build each of those lists. And in general, whenever we have 2 to the k lists with 2 to the m minus k elements, that'll go down to 2 to the k minus 1 lists, and it'll have 2 to the m minus k plus 1 elements each. So since I've got 2 lists with 2 to the m minus k elements, or 2 to the k lists of that, each one of these will take 2 of these to become 1 of these. And that means I'm going to have to do 2 to the m minus k plus 2 to the m minus k minus 1 comparisons for each one of these lists that I'm merging into. And I can multiply that by 2 to get 2 to the m minus k plus 1 and have that minus 1 there. And I've got to do that 2 to the k minus 1 times. And then I've got all my values of k, which will go from 1 to m. So let me show you how there's a PDF that I will email you that you can kind of see how I count these comparisons up. And if you can't find it, just ask me and I'll send it to you. Okay, so let's express that as a sum. So k is going to go from 1 to m, and really k goes from m down to 1 because I start with 2 to the m lists. And then there's that number of comparisons for each merge. There's the number of lists that I merge into, and I do that for all those k's. I can multiply this through there, distribute that 2 to the k minus 1, and I can break that sum apart into the sum of 2 to the m, where k goes from 1 to m, and 2 to the k minus 1 as k goes from 1 to m. And the sum of 2 to the m doesn't have a k in it, so it's just m copies of 2 to the m. And this is a geometric sum here. There's a formula for that to get 2 to the m minus 1. But remember, 2 to the m is equal to n. And so I can replace that with an n. And log of n equals m, so I can replace m with log n. And this will also get replaced with n. And there's my justifications. And the fastest growing term in this polynomial, or this expression, is n log n. So this talks about the geometric sum here. So this is a pretty good. This is actually in the class of the best sorting algorithms that are used. There's another sorting algorithm that has similar performance called quicksort, which I don't require you to know about, but some of the suggested homework problems point you towards it. And that is our discussion of merge sort.